Yesterday we talked about these properties on the right here. I'm just going to tell you, just like I give you this advice, you need to know those properties. Not kind of know them, not occasionally know them. You've got to know them. And I will tell you that it would be in your absolute best interest to know what the property is called. The product property, the power property, the power of a product property, negative exponents, quotient property, and the power of a quotient property. It's in your best interest to know them. The honors kids are doing the same stuff you're doing right now. It's just harder. And when you mix up the properties and you're not sure how they work, you're toast. It just isn't going to go away. So these properties off to the right here, please learn them backwards and forwards and be really comfortable with them. And in addition, what we did yesterday, switching from exponential to radical, you want to be able to go back and forth on those. So in this, we're kind of just looking at this as a review. You have a base to a power, base to a power. What do you do with your powers? Together. Okay? So if we're simplifying right in the fractional exponents, excuse me, you're probably going to want to change this to the 3 over 12 power and the 4 over 12 power and get it to 7 to the 7/12 power. Again, one of the weaknesses, we know they're weaknesses, but we know that this right here has to have same denominators in order to have them. Is there anything you can do with 7 over 12 in terms of reducing? No. So we leave it like that. So we're looking to simplify expressions. Make sure you read the directions because it's usually going to tell you what form to put them in. Now notice, this one we have different bases. You can't multiply the 6 and the 4 together because they're different bases. What can you do in the second problem? Distribute your power. Use the power of a product property, which is going to give you 6 times 4 to the 2/3. 6 times 4 to the 2/3. And at this point, you can just leave it like that. There is more simplifying we could do, but it's not critical for us to do right now. One like this is even better because it's the same idea, but this becomes 4 to what power? -1. When we multiply these, you're going to get -1 here, and 3 also to the -1 power, which gives you 1 over 12. So that one's going to simplify all the way. Any questions on these two? We're using the product raised to a power, so it's the power of a product property. We multiply these two exponents in both cases. Does that work for everybody? Be careful. Try number 4. Really easy, but it's setting you up to make a mistake. I want to take you back. Hang on, Jonathan. I want to go back to this. I don't really like the way the power of a product is done because it doesn't really show you what happens if A and B are raised to powers. So you might want to include, maybe do A to the R, B to the T, raised to the M power. And realize that when you have a product to a power, you're multiplying your power. So it's A to the M times R power times B to the T times M power. Right? You're just multiplying exponents just like you would in this power property right here. You're just doing it twice. So keep that in mind. And I want to point out one other thing. This is where we are. So I'll erase this, but I want you to know that this is 5 to the 113th power, the way most of you write it. So if you use this slashy fraction thing right here, you need to change that behavior right now. If you use it on a test, for every one you use on a test for an answer, I'm going to take minus 10. So if you use it 12 times, you're going to owe me points on this test. Do not use this slashy fraction in here or in any other math class again. Write it 5 to the 1/3. I don't care if you have to kill extra trees to do this. Use up the paper. We'll recycle it if you want. But this needs to not happen. Okay? Some of you are so afraid you're writing 5 to the 1/3. You're giving me this because you don't want to let your pen touch the blue lines on your paper. Look, if you go across those lines, it's not going to burst into flames, I promise. And if it's an issue, get some stinking blank paper, but don't use that slashy fraction thing. How's that? Everybody got that?
What if it's not slashy to like the side somewhere?
No slashies.
Slashy, but like it's like that, but it's a little bit slashy and yeah.
Okay, no slashies at all. We want conservative horizontal fraction bars. Okay? On the weekends you can wear slashy, but in school we want this. Okay? I'm telling you this for your own good because really as you go up and as we get more complicated, when you do the slashy, and let's say you had this, it's very difficult for me to tell, do you mean this or do you mean this? And I think we can all agree that that's where we will get into a lot of trouble with confusion. Oh, but I can just put parentheses. Of course you can. But if you do this, I'm taking 10. Don't do it. All right? It causes way more trouble than it's worth. And nowhere is this a symbol in mathematics. That's not a mathematical division symbol. Yeah, but this, I'm just telling you right now, this is not a symbol that we use. And I know on some of your calculators it does that, but some of them, they don't. You know why they changed them? Because it's not a mathematical symbol. You know why we had them there in the original calculators? Because it was easier to program that way. All right? So I know that you have the habit of doing that. Break the habit. All right? This one, this is, remember, it's 5 to the 1st. So you're going to end up with 5 to the 2/3 power. Big exponent, little exponent. Big one minus little, 5 to the 2/3. Yeah. I'm sorry? Let's look at our properties. Got to memorize your properties. A to the m over a to the n is a. You don't change your base to the m minus n. If it was 1, then your answer would be 1, wouldn't it? So no matter what you did, you would always get an answer of 1. If it was 5 to the 100th over 5 to the 1st, you would say, oh, that's 1. And we know it's not. Right? This one, the temptation is, oh, let's distribute the power of 2 maybe. No, let's not do that. Okay? You can't subtract your exponents because your bases are different. But because your exponents are the same, what you can do is you can say 42 over 6 to the 1/3 power. The powers are the same. We can go backwards and say, oh, it's 42 over 6 to the 1/3, and that whole thing will be squared. What's 42 over 6? 7. So you're going to get 7 to the 2/3 power. When you multiply your exponents, you get 2/3. 42 over 6, 7. Are there other ways to do it? Yeah, but you got to get 7 to the 2/3.
So, if you did distribute the 2.
Then you would have had a 2/3 here and a 2/3 here.
And could you simplify that?
Then you could have pulled this right here, except this would have been a 2/3, right? Then you would have got 42 over 6 to the 2/3, or 7 to the 2/3, right? Did you get this?
No, I just left it for 2/3 over 6.
Okay, you have to go all the way down to 7 to the 2/3. What else? You take that phone from me if you don't put it away. For example.
42 to the 1/2 over 6.
Yeah, you can.
So you just leave it.
Yeah, there's nothing you can do. The only reason why this works is because the powers are the same. Okay, gotta have the same powers. But now we get into some further examples here. The key here with all our properties are the bases the same or are they different? Here, your bases are different. So you can't combine the 5 and the 7 and the 1/3 and the 1/4. You can't do that. What can you do? Distribute the power, right? So you're going to get 5 times 7 to the 3/4 power. That's all you can do. But in the second example, the bases are the same. What do you do with your powers? Add them. So you're going to get 2 to the 5 over 4 power. Now some of you look at it and you say, no idea how you got 5 over 4. And if you're in that boat and you don't ask the questions, I don't know what to tell you. You've got to start asking, how did you, and then fill in the blank. I'm afraid I'll look stupid. You know, you're going to look stupid the day of the test. Now you look smart because you're asking the right questions. The day of the test, when you never ask those questions, now you're going to look stupid. What am I going to do with my powers here? Which property do I have going? Do you know what it sounds like? Can you read the property to me? Do you have it written down anywhere? You might. If you did, I would hope you would learn that it's the product property in which you add your exponents. Are you familiar with this? This is called the product property. Right? So as long as my bases are the same, what do I do with the exponents? You add them. Now I can do it in my head. If you can't, you would have to take 3 over 4 plus 1 over 2 and get a common denominator. 3 over 4 and 2 over 4, right? And when you add those, 5 over 4, that becomes your power. The base doesn't change. And I know in Algebra 1, I really have to battle kids not to write down 4. 2 times 2 is 4, Mr. Locke, right? Yes, I understand that, but that's not what this property tells you. The base doesn't change. Same with the quotient. The base doesn't change. So I battle my Algebra 1 students. 2 times 2 is 4 to the 5/4. No. The base stays the same. Okay? So be careful with that. Be careful with that. Any questions on either of these? This?
Yeah.
No way. But if you keep getting the wrong answers here, you might consider showing the work. But 3 over 4 plus 1 over 2, do it in your head. I'm totally fine with that. I'm only showing you that just to make sure we're all on the same page. Why can't you, the collective you, do this? Because you've never been forced to do it without a calculator. At some point in time, a lot of math teachers, especially elementary school and middle school teachers, they have a hard time explaining how to do it, and so they just say, just do it. here, use your calculator, this is all you do, punch and play. Okay, it's not, doesn't do you a darn bit of good. It's easier, but now you're in Algebra 2 and you can't add a 3/4 and a half.
Where can we find all the properties in full?
I have no idea. We're in section 2 today, right?
Yeah.
So in section 2, you have properties, and in section 1, in your notes, if you go online, all the properties were yesterday. We're revisiting most of those properties today. They were on the first slide here.
Okay.
Right? What page? 420. You have a book right in front of you. This one is always tricky. The one on the left is always tricky. We just did one just like it a minute ago, right? What do you have to remember on this C question?
That the power of 3 is 1.
This is a 1, okay? Where is the bigger exponent, top or bottom? And when you subtract 1/3 from 1, 2/3. Remember, we don't cross out the 3's. The base doesn't change. 3 to the 2/3. What property is it? This is what you got to work on, quotient property. Now, a lot of you are going to blow it off. You're not going to learn the properties. You're going to try to fake it. And most of you are going to do just fine faking it. But I'm telling you, you're putting yourself in harm's way. Learn the names of the properties and what they do. Okay? You don't want to be this person faking it all the time. Can we divide the 20 by 5 on this one? Why not?
Yes.
They're different bases. You can't just, when they're raised to powers, just say 20 divided by 5 is 4. However, since our powers are the same, we could rewrite going backwards, if you wanted, and put 20 over 5 to the 1/3. And that would work great. You'd get 4 to the 1/3 to the 3rd, which is 4. Or you might just say, whoa, 1/3, 1/3, and a 3. We could just multiply and get 20 over 5, which is 4. I don't care which way you're thinking this through. It doesn't matter to me.
So if you get one of those problems and the exponents are the same,
Then you can't do that. Then you would have to distribute. So you would have to go here and here and get 20 to the 1st over 5 to the 1st. Of course, if they weren't the same, you'd have different powers after you distribute the power. Then you would have to see, is there anything you could do? And there probably isn't going to be much you could do. So for example, if this were a 2, okay, now we could distribute and you'd get 20 on the top, but you'd get 5 squared on the bottom, which means you'd have 20 over 25, which is 4 over 5. Does that make sense? So we're kind of, you're forcing you back into that arithmetic stuff. We don't want to, and I'm not saying that's not going to happen. It absolutely could happen. So that's going to give me a 4. And this,
So are you okay with us going straight from the
No,
problem to
no,
4?
no. No, show me something. They should either show me this, or you could have done the 20 over 5 to the 1/3 all cubed. From there, I would be okay with you going to 4, because you could multiply those two and get a 1 and 20 divided by 5. And I'm not trying to be a pain with that stuff. We are all at different levels of what you can and can't do in your head. I don't want that to be the issue. I want to see what you did. Show me. Anybody else had a hand I missed? Okay. Now we're working in radicals. Radicals behave the same as fractional exponents because they're the same thing. So now you're applying the properties of radicals. So we had all these properties of exponents yesterday. The same properties apply to radicals, and they have the same names. This is the product property for radical. Radical times radical. Product property. You can take the radicands that are separate and put them together under 1, or if you're under 1, you can separate them into 2. This property goes in both directions. That property, the product property works both ways, as does the quotient property, works in both directions. So the product property for radicals and the quotient property for radicals works just like it does when we look at the quotient property for and the product property for exponents. It does a lot of the same stuff. So when you look at the first example, the cube root of 12 times the cube root of 18, when you multiply, you can put them and be the cube root of 12 times 18. What's 12 times 18? 216. And the cube root of 216 is 6. Shalaki, I don't know the cube root of 216. Right? If you don't know that the cube root of 216 is 6, then you're going to have to go and tree it. You got to think, you got to be able to tree these. So saying you can't tree them, then that's a problem. What goes into 216? 2 and 108. 2 and 54. 2 and 27. 3 and 9. 3 and 3. What's your index? 3. That means we're playing poker and you're looking for 3 of a kind. Every time you have 3 of a kind, 1, 2, 3, you put them back together and you get a perfect cube. 2 is the cube root of 8. Okay? 3 of a kind, 1, 2, 3. 27 is a perfect cube. The cube root is 3. 2 times 3 is 6. Okay? So if you look at the cube root of 216, you could say it's the cube root of 8 times the cube root of 27. These two you should know. How do you know that those 8 times 27 is 216? You've just treated it. You factored it. 3 of a kind gives you the perfect cubes. Cube root of 8 is 2. Cube root of 27 is 3. Cube root of 216 is 6. The more you do, the better. You want to do yourself a huge favor? Leave your calculators in your backpack. All you are doing by using the calculators is you're preventing yourself from honing these skills. You're not willing to suffer. You want to run a marathon, but you're going to do it on a bike or in a car. Run the dang marathon already. Okay? Putting yourself at a huge disadvantage every time you try to take a shortcut.
How come for when you have the same exponents you add, but for this you have the same radicals that you just multiply?
You're only multiplying the radicand. So when what we're looking at here with the exponents was this: a to the m times b to the m is the same as ab to the m. It's the one where you're distributing the power of a product.
Okay.
So this times this is like this, and the power would be 1 over n, 1 over n, if you think about it with fractional exponents. Okay? So same idea, and same thing with the quotient. It's the quotient of the power of a quotient. This is the radical of a quotient. Same idea. Good question. So based on what you learned yesterday, if you have the fourth root and the fourth root, we can just do one big fourth root of 80 over 5. What's 80 over 5? 16. What's the fourth root of 16? Isn't it plus or minus?
Yeah.
Why not? It's not yes, it's no. Why is it no? It's not an equation. Very good. If this were an equation where x to the fourth equaled 16, and you fourth root both sides, then you have to do the plus or minus. If it's an even root on both sides of an equation. Okay? And that's one of those things you want to make sure, am I talking about an equation? And if I'm not, gotta make sure that we get that in order. Yes? Slower? Okay, we're now going to talk about simplifying radicals. And there are several criteria that you have to meet whenever you give your answers that are in radical form. And we'll talk about what you do with exponents and how you handle those as well. But for radical form, here's some basic things that you can't have in your answers. You can't have a fraction under the radical. Okay? No fractions under the radical. Jonathan, we good? So you can, this is simplest radical form. No fractions under a radical. No radicals in the bottom. No perfect nth factors of the radicand. What's that? Nth means if you're doing square root, second root. If they're cube roots, no perfect cube factors.
Nothing above first.
No, it's whatever. This one's going to be perfect cubes. N is the index. Whatever number is here, you can't have any perfect cubes factors. Good?
Yeah.
You can't have any perfect fifths in this one. Okay, it's whatever your index is that you say, well, we can't have any of those perfect factors. That's why yesterday we talked about you got to memorize your perfect squares, your perfect cubes, and your powers of 2. And even some of your powers of 3 would be helpful. Okay? So the way I do this is I talk about, like the bottom one, I talk about good guys and bad guys. That's what I call that. And we talked about that earlier, right? Way like at the beginning of the course. Okay? So what we want to use is the product property backwards. You want to change this so that you have right here, this is what I call the good guy factor. No, you can't, but he moves out of the way all the time. If you're patient, he will be out of your way in a moment. And on the right-hand side, you put the bad guys. Don't put the good guys on the right, bad guys on the left. It's not going to do you any good. You're going to get confused. Good guys are perfect cubes in this case. Is there a perfect cube that goes into 135? 9 is not a perfect cube, but 27 is. How many times does 27 go into 135? 5 times. That's the bad guy. 27 times 5 is 135. I see it. Tell me. You're making that face. So what the heck are you talking about face? Yes, you most certainly
That's
are.
my face.
No, it's not. You never have the what you're trying to be talking about face.
It's just my normal face.
No, it's different today then. Must be that slashy thing.
I never know what's going on again.
No, that's not true. Are you with me on the 27 and the 5? Why I'm choosing 27? Okay. What if you don't know that 27 goes into 135? What could you do? Tree it. So if you get totally stuck, you need to tree it, and you're looking for a 3 of a kind. Here's your 135. You know what goes in there. 5. 5 times 27. Now, if you recognize 27 as a good guy, great, stop. If you need to do 3 and 9, 3 and 3, and then there's your 3 of a kind, so be it. That's up to you. What is the cube root of 27? 3. And the cube root of 5 stays the cube root of 5. What's wrong with B?
Yeah, radical on the bottom.
Radical on the bottom, no good. These are fifth roots. You can't have a fifth root of 8 in the bottom. But in order to fix it, you do not multiply by the fifth root of 8, because that's not going to help you. So because 8 is a perfect cube, I would suggest that you rewrite it as the fifth root of 2 cubed. Otherwise, you're going to have to work with huge E numbers, and you're going to need a calculator. Okay? If you write it with the smallest base possible, like obviously if this was a 7 on the bottom, there's nothing you can do. You'd have to leave it 7 to the first. What is the next perfect fifth bigger than 2 to the third? What is the next perfect fifth bigger than 2 to the third? 2 to the fifth. So we need, well, I don't care what the number is. What am I going to have to multiply this by?
4.
Not 2 to the fifth,
2 squared.
2 to the second. So you want to do the fifth root of 2 to the second. Now, this is tough stuff. This is confusing. It's something that you really haven't dealt with much except with square roots, not fifth roots, not cube roots. What you're looking for is a power that is a multiple of your index. And the biggest or the smallest multiple of 5 that's bigger than 3 is in fact 5. So I need to figure out what do I multiply 2 cubed by so that I could get 2 to the fifth. And that's 2 squared. Remember, when we're multiplying, what do you do with your powers? Add. So we have to do fifth root of 2 squared, both top and bottom. What is 2 squared? 4. So fifth root of 7 times the fifth root of 2 squared is going to give you the fifth root of, what will that be? 28. Over the fifth root of 2 to the fifth. Take a look at that before we fix it. Is everybody following why it's 2 squared, the fifth root of 2 squared, and why we have a 28 and a 2 to the fifth under the radicals in the next line?
I'm
Yeah.
not sure how you figured out how to multiply
This?
Yeah.
Okay. And that's going to be the rub. And once it clicks in, you're going to be good. Be patient and keep saying, can you say it again, say it again, say it again when we go through these. This is a 5 right here, right?
Yeah.
Now, if you think about it, the fifth root of 2 to the fifth is 2. Okay? The fifth root of 2 to the 10th is 2 squared. And the fifth root of 2 to the 15th would be 2 cubed and so forth. No more radicals, right? It's just like when you did the square root of 9, that's 3. But the square root of 7, nothing we can do. All right? So we're looking at the fifth root of 8. Not a good guy. Now, I don't know very many fifths. Powers of 5 off the top of my head. 32 is 2 to the fifth. 3 to the fifth is 343. 4 to the fifth, 512. And after that, I don't do very well. I mean, I can do more, but I know that 8's not one of them. Okay? But I do know 8 can be written as 2 to the third. If I look at this and I say, okay, I want 2 to the 5th, or 2 to the 10th, or 2 to the 15th, or 2 to the 20th, what would I multiply 2 to the third by to get 2 to the 5th? That's going to be 2 squared. 2 to the third times 2 to the second, we add those exponents, right?
Yeah.
So 5 subtract 3 gives me a 2. That's how I know what to multiply by.
Oh, okay.
Okay? Now, if this was 2 to the 7th, okay, what would the next multiple of 5 be that's greater than a 7? What's the next multiple of 5 that's bigger than 7? Let's do our multiple of 5. Yeah, not helping. Like this is what we normally do.
Well, I know it's 5, 10, 15,
And so if this was a 7, what's the next multiple of 5 that's bigger than 7? We would want 10. No, yeah, I'm not asking, you're answering a different question. I want to know that the next one is 2 to the 10. What would I have to multiply this by to get to 2 to the 10?
2 to the third.
2 to the 3rd. So you would do the 5th root of 2 cubed on that problem. And we're going to see others in a moment. Somebody have a question? Okay? So when I multiplied here, I got to the 5th root of 2 to the 5th, but on the top, 4 times 7 is still ugly. We don't really care. Because the top didn't say we have to do anything special on the top. What's the 5th root of 2 to the 5th? 2. So you're going to get the 5th root of 28 over 2. Guess what the common mistake is going to be?
Oh, 28, 2. That makes.
Guess what the common mistake is going to be? No, they won't do. I mean, here's my answer. You did a great job. What else are they going to? What are you going to put next? And give me the 5th root of 14. And you can't divide this 28 by 2. More?
Yeah.
Tell me when.
The
The answer was in red. The 5th root of 28 all over there. 5th root of 28 all over there. Questions? This is a hard problem right now. On a scale of 1 to 10 in a week, this is going to be a 2 for you. You're going to be able to do this problem in your sleep. Right now, it's confusing to get used to these new indexes. Okay? It's very confusing. Take a look at these 4 and see how you do with these. Again, there's not just one way to go on this. So don't feel like there's only one way to do these. There's more than one way to do that. 27, how could you rewrite it? 27, the number 27. 3 to the 3rd. So if you wanted, you could do this as the 4th root of 3 to the 3rd times the 4th root of 3 becomes the 4th root of 3 to the 4th. 4 divided by 4 is 1. So that's going to be 3. That's one way to do that problem. You could have multiplied these two together and said, oh, that's the 4th root of 81. What's the 4th root of 81? 3. That's fantastic. How you get there does not matter to me. There is more than one way. I can't show you all the ways. Okay? If you got 3 and you did a legitimate algebraic method, cowabunga awesome. What should I do with 7? What could I do with 7?
Times it by the cubic root of 2 squared.
You could, and that would get rid of the radical on the bottom. And, well, it wouldn't get rid of the one on the top, but yeah, we could put this all under one cube root since it's cube root and cube root, and you get 250 over 2, right? What's 250 over 2? And that's a good guy. What's that? 5. So although that works, that would be something that I would do if they weren't both cube roots. And if 2 didn't go into 250, I wouldn't do this. I would go with what Jonathan said. This has a fraction under a radical that can't be reduced. So now we do the opposite of what we did here. And we separate it. This is the 5th root of 3 over the 5th root, and I'm going to write it as 2 squared. Now we're going to go with the path Jonathan chose on the previous problem. Whoops. I need to get 2 to the power of 5, so I'm going to multiply it by the 5th root of what?
2 cubed over
2 to the 3rd. Top and bottom. What is 2 cubed? So on the top, we're going to get the 5th root. What do you get on the top?
5th root 24.
24. On the bottom, you get the 5th root of 2 to the 5th, which is 2. It's a process. You have to be willing to go through, boom, boom, boom. Down the page, no equals, follow the process. Is there only one path? Not a chance. Not a chance. The cube root of 5, nothing you can do. How about the cube root of 40? Other way around.
8 times cube over 5.
Good guys and bad guys. We're looking for perfect cubes. Hopefully you memorized those cubes last time. What is the cube root of 8? Now you have like terms. It's the same index, same radicand, combined like terms. How many of them are there?
3.
3 cube roots of 5. Any of these 4, any issues? How many cube roots of 5 are here? Right here. How many? 1. It's invisible, right? How many are here? How many cube roots of 5 are here? And when you add them, there's 3. It's like doing x plus 2x. That's 3x. Oh, right there? 5th root of 24 over the 2. And again, your goal is no radicals under the fraction, or no fractions under the radical, no radicals in the bottom, and no perfect nth factors of the radicand. So in other words, there can be no perfect 5th factors of 24. And there aren't. The biggest you can get is a cube out of that. Okay. Anybody on any of these 4? Ask the questions. It'll help you get through this initial stage. Don't ask them, you're going to get lost fast.
For cube root of 250 over the cube root of 2.
Uh-huh.
I did it. I came out with 250.
Did you get 5 as an answer? Okay. In the way something's wrong with what you're doing.
Yeah, I times it by the cubic root of 2 squared. And then I just came out with 500 up top.
500 cubed.
Got a cube root.
You wouldn't get 500, you'd get 1,000.
Right. I just.
Right? And cube root of 1,000 would be good. That would be 10. And then on the bottom, you'd have the cube root of 2. And 10 divided by 2 would give you 5. That way it works. It's not the most efficient, but it absolutely works. Somebody else? Okay. Remember, like terms have the same index and the same thing under the radical, the same radicand. Ones that are not like terms have different indexes. If they have different indexes, not like terms. If they had different radicals, they would not be like terms, even if the indexes were the same. If the radicands are different, they're not like terms. If the indexes are different, they're not like terms. These are like terms, these are unlike terms. If they are like terms, you add the coefficients. You don't change the index, and you don't change the radicand. 3x plus 5x is 8x, not 8x squared. 3/4 roots plus 5/4 roots is 8/4 roots of whatever's under there. They don't change. It's just adding and subtracting, combining like terms. So if you're adding the 4th root of 10 and 7/4 roots of 10, what would you get? 8/4 roots of 10. Okay? 2 times 8 to the 1/5 plus 10 times 8 to the 1/5. 12. 8 to the 1/5. Can you do 12 times 8 and get 96? Make it smaller, make it simpler. Can we do the 12 times the 8? Why? Yeah, parentheses isn't the reason.
The power.
Because 8 is being raised to a power, you have to do the power first.
Or operation.
Okay? You need to follow order of operations. Cube root of 54 and cube root of 2, are they like terms? Yes. No. You have commitment problems, don't you? They do have different radicands, so they're not like terms. Are there any good guys that go into 54? 27 is a good guy. So if we switch this up and do good guys, bad guys, what is the cube root of 27? 3. So you have 3 times the cube root of 2 minus the cube root of 2. That's what a lot of people will do today. They'll say, oh, that's 3. The cube root of 2's are gone. 3 hot dogs, take away 1 hot dog is, you just have the number 3 floating in front of you. You got nothing to eat, right? If you had 3 hot dogs and took away 1 hot dog, you'd have just a 3 floating there, right? What would you have? 2 floating there? 2 hot dogs. You have 3 hot dogs minus 1 hot dog leaves you 2 cube roots of 2. Don't change the rules because we have these funny radical looking things. You got 3 of them, take away 1 of them, leaves you 2 of them. That's not going to change. 3 minus 1 is 2 of those things. Whatever the things are, they just happen to be this ugly cube root of 2 deal. I don't know. You look like you were going to say something. I know, it's just your face. Right?
You said that 3 hot dogs minus 1 hot dog equals 2 times the cube root of 2.
Here's what we started with. 3 of these minus this gives you the answer 3. Let's make that sound about this. I know, but the joke hasn't got out of that table yet, so we're trying to catch up here. Are you good or not good? Good or not good? Good. Holy cow. The one on the left, is it simplified? Why not? Correct. The square root of x to the 9th. The common mistake on the first day, today, is to say, oh, Mr. Lockley, that's x to the 3rd. We are not square rooting the 9. We are square rooting x to the 9th. And x to the 9th is not a perfect square, because 9 divided by 2 is not an integer. So we need to do good guys and bad guys, and the good guy is x to the 8th. The biggest number that's smaller than 9 that the index divides into. So I need something smaller than 9 that's divisible by 2, that would be an 8. If I take x to the 8th out, how many x's are left? X to the 1st. What is the square root of x to the 8th? That's how we simplify. But you have to separate good guys and bad guys. And x to the 9th is not a perfect square. X to the 16th, on the other hand, is a perfect square. What is the square root of x to the 16th?
X to the 8.
Okay, I heard two
Plus
answers.
or minus x to
No, it's not a equation.
We take 16, and do you take the square root of this, or divide it by 2? Divide it by 2. So you're going to get x to the 8th. 16 divided by 2 is x to the 8th. Remember, x to the 8th times x to the 8th is x to the 16th. You add your exponent. So x to the 8th is the square root of x to the 16th. Okay, how about questions on that? You have to be able to separate these. Okay.